So the deal, we've been talking about black holes, and I think I already mentioned the reason they call them black actually has to do with light, that light cannot escape a black hole. And we talked about escape velocity from the Earth, and honestly, nothing can go faster than the speed of light, and I'll kind of try to tell you why that is coming up. Okay, so black holes are black because light can't escape them. So it's kind of interesting if you think about normal objects, I guess 4 objects. Normal matter, like this table, okay? And then we think about a white dwarf we said is very dense, a white dwarf. Basically, the thing about a white dwarf, though, is it's normal atoms. Basically, you have the nucleus and you have electrons, okay? The thing about then a neutron star is, and I kind of stomp my feet like this, okay, it's squished down matter. Basically, it's so squished that electrons and protons have combined to make neutrons. So basically, we have neutron soup here. We don't have regular atoms. Okay, I mention that because that last little bit about a black hole, basically black holes, you've taken your matter and you go, you just squished it down even more. So now neutron degeneracy doesn't stop the collapse of this material. So you're like, what is that? I mean, it's not atoms. It's not neutrons anymore. What is it? Well, it keeps its mass, okay? But other than that, it's kind of something a little more exotic. So, over here to the black hole, okay, when we talk about the anatomy of a black hole, we already talked about something called the event horizon, I think, didn't we? Okay, good. And this thing that actually the matter has all fallen to a point, usually it's a point, sometimes it's a circle, singularity, but the point of singularity is where the stuff falls to. And I kind of lose track of what videos you've already seen, but we can kind of think of where that singularity is, where that black hole is. Basically, the fabric of space and time, which we've talked about a little bit, has kind of collapsed in on itself. Okay? So, I'm going to play this, see if we've seen this one before. You know, the person falling into the black hole would look, from our perspective, going really slow. And it's true. Okay, we're going to talk about that. That's actually called time dilation. And from that person's perspective, we'd be like, really fast. Okay, it's like an Einstein thing, and it's provable. And then the other thing he talked about was kind of the something we call gravitational redshift, and that's going to happen too. That's coming up too. But what we see here are different, yeah.
You said that nothing escapes black holes, but why do they always show the stuff shooting out either of the poles then?
The stuff shooting out either of the poles, that's a good question, and we're going to talk about that, is kind of, do you remember where we talked about like accretion disks? Mm-hmm. Okay, that is kind of like energy that is kind of in Q, okay, and it's beyond the event horizon, but it's created by the commotion that the black hole is.
So it's not right on the black hole.
Right.
It's not coming out of the black hole.
Right.
Okay.
It's not coming out of the black hole, but it looks like it is, but it's on the other side of the event horizon.
Okay.
Yeah. But it's created by the black hole, too. Yeah, those jets. So these are the fabrics of space and time, and I think we looked at this on Wednesday, that you can, if you have an object that is the right density, and I go over here and I stomp on something and make it the right density, okay, squished packed density is related to mass and volume, okay? Then you can create a black hole. And there are black holes in the center of galaxies, like the Milky Way has a black hole. You can create a black hole at the explosive end of a massive star. Okay. Okay. So I added the year 1905. The older I get, the more I'm like, oh, I guess history really does matter. Okay. Back in 1905, Einstein came up with his first of 2 theories about relativity. Okay. This is his special theory of relativity. And in math, all the time, if you're going to do a proof in math, I don't know if you're familiar with proofs, a lot of times you set the terms, you set the guidelines, you set the assumptions out front. And so this is what Einstein did. So when he talks about relativity, there are 2 assumptions. And I think I'll just talk about him. Okay. We're going to be talking about frames of reference, okay? And in the video we just saw, there were two frames of reference. There was a frame of reference near the black hole, and there was a frame of reference away from the black hole. That's two frames of reference. So regardless of what kind of look around you, that's your frame of reference you're in. Okay, your measuring device, and we're going to talk about three things to measure. We're going to talk about length to measure, time to measure, and actually a scale, basically mass to measure. If you're in, regardless of whatever frame of reference you're in, those three things, your ruler, your watch, and your scale, all work the same. So I think what works well is if you guys have a stationary frame of reference, and if I'm walking, okay, this is my frame of reference, okay? And actually, probably better to the point, I could be like on a boxcar or something, like a little train thing that's making me move. Okay, that's my frame of reference. I'm moving. You guys are stationary. Okay, we both have rulers. We both have watches. We both have scales. The other thing is that speeds aren't additive when it comes to objects emitting light. Okay, so I have a blank page to kind of show you what I mean by additive. But light coming, regardless if I'm moving, okay, or if I'm sitting still, okay, when an object sends light to me, it's always traveling the speed of light, which the symbol for the speed of light is the letter C. So let me kind of show you what we're used to with regard to being additive. I wonder if I have this in my, let's see if this will work. I know this looks like a strange drawing, but just bear with me. Okay, so I drew this last night. So here's the deal. This is me. I'm standing still, and this is, I dare say it's a little person, but like a little kid on a moving boxcar. Okay, so his frame of reference is moving. My frame of reference is standing still, and this little kid is throwing a ball. Now, I mentioned additive velocities or additive speeds. So if, heaven forbid, he's on something that's going 40 miles per hour, right? Okay, and let's say he's a top-notch thrower, okay, and he can throw the ball at 20 miles per hour, okay? So he's standing on this thing, and this thing is moving 40, and he's throwing it 20. Okay, see, to me, I would add those two together, and I think you'd be okay. I think Mr. Day would be good with that. So honestly, the speed I see the ball moving at is 60 miles per hour, okay? It's additive. But light is a different thing. So here's my little drawing down here, okay? I know that looks like a tree, but hopefully you'll think more like a light bulb, okay? So that's supposed to be my little light bulb, and it's emitting light in all directions, including me. I'm going to be standing over here again. And those little beams of light, okay, one of the cool things about light is we know that the light travels at the speed of light, okay? So we're going to go ahead and make this light bulb go on a train too, okay? And we're actually going to make this train, okay, traveling towards me, but it's 25% or 0.25 the speed of light. So here we go. I'm over there, and with regard to those photons of light coming from that beam, they're going at c, the speed of light, but they're on something that's moving towards me at a quarter the speed of light. So my estimation, that'd be 1.25. 1.25 times the speed of light is how fast it would be moving towards me. Okay, it's additive. And the thing is, this is not how it works. Nothing can go faster than the speed of light. So there's got to be some adjustment. And it's called simultaneity. And actually, it's the word on the top of your next slide. Simultaneity. And I've got some videos to try to kind of explain what that is. Oops. Okay. So what I just tried to explain with my second drawing down there is what's being explained here. So here we have somebody in a very fast convertible. You know, half the speed of light is very, very fast. Okay. Things don't go half the speed of light. But if we could, right? Now, Here's the deal. Here's the photons, like I had on the little moving train a little bit ago. So those photons, as seen from this person just standing still, okay, that light or those photons are going the speed of light. From the person in the fast car that's driving half the speed of light, those photons from that lamp cannot be going 1.5 times the speed of light. They also are going the speed of light. So you're like, okay, what happened to that person's speed adding to the speed of light? And the answer is simultaneity. Okay, so let's see. All right. So those are, if they aren't confusing enough, those, remember, are the assumptions. Okay, the two assumptions are that your frame of reference, your ability to measure length, to measure time, to measure mass is the same, whether you're moving or whether you're stationary. Okay. Now these are the three outcomes, and they're kind of cool. Okay, I've heard this one described as length contraction, and that might help. The word contraction, length contraction, might help. If you read this description, basically it says that, and I'll go ahead and you guys can sit still and I'll go ahead and move again. Now the faster I'm moving, really I have to move pushing the speed of light, okay? But my length will contract. Will it contract to me? No. Will it contract to you? Yes. Okay, relative to your reference, my length gets shorter. And I know students kind of look at this and like, yeah, it gets shorter because you can barely see it because it's so fast, because it's moving so fast. No. If you were to be able to measure the length of anything within my reference or my reference itself, which is like the train, it's getting shorter. Okay? Yeah. Length contraction. So the faster something goes, the more its length gets shorter. And so approaching the speed of light, it gets to basically no length at all. Strange, 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 strange. I'm going to show you another video here. This one's called time dilation. And this one actually, a little bit ago when we said that the person who's going to be spaghettified and fall into the black hole actually was going way slow compared to you guys who were stationary, okay? That's time dilation in effect. So here, though, not a black hole, but if something's moving fast like me again, okay, time, and actually this little bit I'm going to show you is going to prove this to you, hopefully, but my watch will slow down. You're like, oh, maybe there's a malfunction with your watch. No. The time within my space, if my point of reference is moving, will unfold more slowly. Okay? Time goes more slowly. So if you've ever heard about the whole, you take a pair of twins, okay, take two guys or girls who are born at the same time, and one stays on Earth and one goes traveling, okay? If this person's traveling at pushing the speed of light, okay, while they're gone, if their frame of reference is going fast like that, actually their time is unfolding more slowly. So if they go full round trip, come back, actually they have aged less because they've been in the frame of reference that was moving. Okay. So here we go. Here's a little video. Mass is infinite because you get fat, you get more and more. Don't get fatter. you get more and more massive. Okay. So, all right. So that was Einstein's special theory of relativity. His general theory of relativity, published 10 years later, okay, has some outcomes, and we'll talk about those. But just kind of in general, we'll kind of compare Newton's laws of motion and Einstein's, the way thing is with regard to space and time. So if you remember, Newton actually, after Kepler, talked about how gravity affects. Newton was really great in talking about how, oh, this is a planet orbiting a star, okay? He got that, right? And we used Newton's laws to actually, still today, I think we talked about, to understand if we want to go to Mars, we use Newton's laws to say, well, we're going to swing around this planet and go, because we know gravity's going to do that. We use Newton's laws. But For more exotic things, like something that is very dense, like a white dwarf neutron star or black hole, okay, kind of warping the fabric of space and time, or something's going very fast, okay, we need to use Einstein's laws. Okay, so outcomes. Outcomes of now his general theory of relativity. So we said that in the frame of reference, like a plane that's moving fast, we said that time is going to click off more slowly. The fabric in space and time unfolds more slowly. Gravity also has an influence on how time unfolds. It's just amazing. And so, like I was thinking about this lecture, and the other day, and we were feeding the cats at home, and I'm like, you know what? I think time is really going very fast in our house. So I'm like, so if time is going very fast in our house, okay, that must mean, and I'm going to kind of go to this second scenario, that must mean that we have some extra mass or something. So what you see is a more massive Earth and a less massive moon, right? More massive, less massive. And what you see over here are two clocks that start at 3. Over here, you let those clocks run. And notice that on Earth, it went to 3:20. I guess it would be this way. We're losing mass. On the moon, it went to like 3:22. Okay, so I'll go ahead and add this to this. Time went faster, okay, for less massive. Okay, less gravity. Does that make sense? And actually, that is provable too. So the way that time is unfolding around the moon is faster than it's unfolding around the Earth. So put another way, more gravity slows time. I guess I should be putting to that. Okay, that's one of his outcomes. I'm going to play you, see where it says bends? I'm going to play you this little video. And, you know, it's not every year that we have a solar eclipse like we had this fall. But back in 1919, somebody busted his butt to watch the solar eclipse, and this is why. Okay, basically during the solar eclipse, and you're going to see, so you have to watch quickly because they don't have it up there very long. But during a solar eclipse, which is weird to me, he actually could see stars beyond the sun. I can't imagine that. Now, the one we saw was not a total eclipse of the sun. It was a partial eclipse of the sun. Okay? But when the whole disk was covered, he actually could photograph stars. Here's the deal you're going to see on this little video, is he photographed a star that was hiding. He photographed a star that he shouldn't have been able to see. And what happens with objects that are massive like the sun, I know it's not a white dwarf or anything, but it's pretty massive. It makes a dent in space and time, and so light actually bends around. So all the time, this starlight is actually being bent around, okay? So its last known trajectory, actually, it appears like it's over here, even though it's here. So I thought if he can go out of his way in 1919, travel, I think that was shortly after World War I. I don't know, but it was kind of dangerous, I think. We can at least go out on the hill and watch our solar eclipse. Actually, gravitational lensing uses this effect. So, gravitational lensing. Gravitational lensing allows us to actually see, well, lensing kind of magnifies things, so it allows to see distant objects. Okay, the other thing, just kind of proof of the fabric of space and time being warped, kind of like it is for us to see a star behind the sun, is this. And like I think this slide says, this is exaggerated, but kind of the dent that the sun makes in the fabric of space and time actually can be seen in how Mercury orbits the sun. It's kind of a kind of strange thing. Okay, so Neutron star or white dwarf, that would be kind of these two objects. That's normal material. This is a white dwarf. This is a neutron star. And this is actually a black hole. So it has a significant dent in the fabric of space and time. And we can actually see that if we take a light and move that light closer and closer to the white dwarf or neutron star. So here the light is sufficiently away from the object. And the closer we get it to the object, what's happening is that light going in all directions, and one direction is in the direction of the observer. The closer it gets to kind of that dent in the fabric of space and time, the more it has to fight to get out of kind of this gravitational well sort of situation. And so actually, I'll put, to emphasize this, up here at the top scenario where it is actually the closest, it has to, I'm going to say, use energy to get out of gravitational well because it's closer. So you're like, well, how can I see it losing energy? Well, we talked about kind of wavelengths. The color of light that we see is an indication of the energy it has. And the mnemonic device, Roy G. Biv, okay, if we kind of put it backwards like that, we would say that red has the least amount of energy, the longest wavelength, and the violet has the greatest amount of energy. So as we observe this kind of getting redder and redder, that's what we call gravitational redshift. It's losing energy. All right. So I'm trying to see. Yeah, I don't think I'll necessarily play this animation for you. If I were to play it for you, we have two spaceships. One spaceship is falling near the black hole. Okay, that's this one over here. And then one spaceship is safely beyond the event horizon. So this is a black hole right there. Okay, and this one actually is falling towards the event horizon, going to fall into the black hole. And this one is safely out, not even going to go into the black horizon, or black hole, event horizon. So this actually, the color is going to appear red, and that's actually, we heard earlier, if you're watching somebody fall into a black hole, remember the guy said the person's going to go really, really, and they're going to turn red. That's gravitational redshift. The other thing is we can see time tick off. Okay, this person out here, notice that this is more time, okay, less time, okay, and this is showing how time slows. Okay, so it's just kind of reinforcing what we've been talking about. So, of course, we would all want to be in the one with the blue time ticking off. Okay. So, spaghettification, the guy who said, you know, we call that, like if you're going to die by a black hole, we call that spaghettification. I'm going to go ahead and play for you how Neil deGrasse Tyson talks about falling into a black hole. He does it so well. You're like, really? So how do we know about black holes? And as I've been kind of talking about normal matter, white dwarf, a neutron star, and a black hole, when I go stomp, okay. So basically it's kind of a critical density, okay, that basically neutrons haven't stopped the collapse. Does that make sense? We've got soup over here. We had neutron soup here. We had normal matter here, right? So basically we need to know how compact it is, we need to know the mass and the volume of an object. So the guy, one of the videos we watched today, talked about the closest black hole. Now there's different ways to get a black hole. There's one in the center of our galaxy called a supermassive black hole, but this is called a stellar black hole, the ones we've been talking about. So actually in the constellation Cygnus, there is a star that is dumping on a black hole. So this might look familiar. This is an accretion disk again. Okay. In this accretion disk, we can actually get some friction to kind of create X-rays. So it's emitting X-rays. Is there something in the center we can see? No. Okay. But based upon the motion of maybe the gas, we know the mass of that object, we know the volume of that object, and we know it's a black hole. It's the black hole candidate, is kind of what he said. Another thing is, so those are X-rays. Now, gamma rays are on the more energetic side of X-rays. So honestly, we really think that gamma rays, a burst of energy in the gamma ray type of energy can be created when black holes are formed. And then this last, this is still that. Okay, so gamma ray bursts we think are associated with the formation or the coming alive of a black hole. And this last slide kind of finishes up. It's kind of interesting because it almost just like, really? So gamma ray bursts, though, be careful because they can actually be the signal of one of two other things, not just the bursts of black holes. Gamma ray bursts are really energetic events. They can also signal or be associated with just that supernova explosion we've been talking about, or something kind of exotic, a couple of neutron stars collide. So that's that. And thank you for your patience. So that chapter will be due on Monday. And we'll start in on